Welcome back. Let's learn about the triple scalar product and parallelepipeds. Alright, so in a previous lesson on the cross product, we briefly looked at something called the triple scalar product. And we're going to look closer at this idea of a triple scalar product in this video. In particular, we're going to see how we can use it to calculate the volume of a certain 3D solid. But before we can take a look at that, we first need to establish what the triple scalar product is and how we calculate it. And so if you take a look right here, we have three different vectors, vector v, vector u, and vector w. Each of them are three-dimensional vectors with an x, y, and z component. And so the triple scalar product between these three vectors is defined like this. It is the result of the dot product between vector v and the cross product of vector u and vector w. All right, so you would perform the cross product between these two vectors, which would give you another vector, and then you would dot product that vector with vector v. And the result of that would be a scalar value that we would call the triple scalar product. Okay, and so that's the basic idea of the triple scalar product. But before we take a look at how to apply it and calculate volume, I do want to show you an easier way to calculate a triple scalar product that will save you a lot of time. All right, because it's fine to calculate it the way I described it, where you find the cross product between vector u and vector w, and then perform the dot product of that vector with vector v, but we can actually combine those two steps into one to save us some time. And so let me show you what I mean. The first thing that I want to do is just take a look at this cross product vector between vector u and vector w. If we take a closer look at that cross product, here's what we'll have. We'll have vector u cross vector w is equal to the determinant of a 3x3 matrix, where we have vector I, j, and k, our standard unit vectors in that first row. And then the second row will be the components of vector u, and the third row will be the components of vector w. So we'll have u1, u2, u3, and then w1, w2, and w3. If we calculate the determinant of this 3x3 matrix, which will give us the cross product between these vectors, we will start by looking at vector I here. We'll cross out the row and the column that it's located in, and then use the remaining four values to calculate a 2x2 determinant that we then multiply by I. So here's what we'll have. We'll have u2 times w3 minus u3 times w2. So u2 times w3 minus u3 times w2. That is just the 2x2 determinant of these four values if they were a 2x2 matrix. And we're multiplying that by vector I. Then we're going to subtract a 2x2 determinant multiplied by vector j, and then we'll add another 2x2 determinant but multiplied by vector k. All right, now for vector j, let's look at that vector. We'll cross out the row and the column that it's in, and then use these four values to calculate a 2x2 determinant. So we'll have u1 times w3 minus u3 times w1. So let's write that in here. We'll have u1 times w3 minus u3 times w1. All right, and then for this 2x2 determinant, which will be multiplied by vector k, let's look at k in our matrix here. We'll cross out the row and the column that it's in, and then use these four values to calculate a 2x2 determinant. So we'll have u1 times w2 minus u2 times w1. All right, so we have u1 times w2 minus u2 times w1. All right, and so that right there is the cross product of vector u and vector w. And if this process that I just went through seemed foreign, if you've never seen that before, if it was a little confusing, I would encourage you to go back and watch my lesson on the cross product, and that should clear things up. But this is our cross product vector, vector u cross vector w, right here in our triple scalar product. And so what we would then do to calculate the triple scalar product is take the dot product of this vector with vector v. So we would take the sum of the product of corresponding components. We would multiply the x components together. So we would have v1 times this component right here. Then we would add that to multiplying the y components together. So we would have v2 times this y component right here. And then we would add that to multiplying the z components together. So we would have v3 times this z component. And so that's how we would calculate the triple scalar product. But do you see how we could maybe make that a little bit easier for ourselves and combine this dot product and this cross product into one step? Well, if you don't see it, I'm going to explain it to you right now. Notice that if we replace each of these standard unit vectors, I, j, and k, with the x, y, and z components of vector v, this calculation right here would be the triple scalar product, right? This is our vector u cross w, and we would be multiplying each of those components by the respective x, y, and z components of vector v in order to calculate that dot product. And so if we just replace each of those standard unit vectors, I with v1, j with v2, and k with v3, we would have the triple scalar product. And so here's what we can do. If we want to find vector v dot this cross product, or in other words, we're trying to find the triple scalar product, what we can do is simply just replace vector I, j, and k with the components of vector v, v1, v2, and v3. And doing that, we'll replace this I with v1, this j with v2, and this k with v3. And so we'll have v1 here, v2 here, and v3 right here. And now we will have the triple scalar product. We have the x, y, and z components of the cross product between vector u and vector w that we are then multiplying by the corresponding x, y, and z components of vector v. That's the dot product. All right, and so hopefully you can see why that's helpful, because now by just setting up a 3x3 matrix where the first row is vector v, the second row is vector u, and the third row is vector w, we can calculate the triple scalar product in one full swoop. We don't have to take this cross product and then perform the dot product. We can just do all of it at once. And that's going to be particularly helpful when we go to calculate volume using the triple scalar product. Okay, and so with that, that's how we calculate the triple scalar product. This is the quickest way to do it, or the shortcut method that I wanted to show you, but now it's time to talk about volume. Okay, so now that you are familiar with the triple scalar product and how to calculate it quickly, or at least a shortcut method for it, we are ready to take a look at how the triple scalar product will allow us to calculate the volume of a particular 3D solid known as a parallelepiped. All right, and you might hear it pronounced other ways. You might hear parallelepiped. Doesn't really matter. As long as you understand what it is, it's fine. And what a parallelepiped is basically a three-dimensional parallelogram. Okay, and what we'll be able to do using the triple scalar product is calculate the volume of this solid. And so let's talk about how that's possible. First thing that we need to mention here is how we calculate the volume of a 3D solid. All right, without memorizing any particular formulas, a very easy way to calculate volume is to take the area of a cross-section of that 3D shape and then multiply it by the height of the shape. All right, and that will give you the volume, assuming that all of the cross-sections for that solid in that particular direction are the same. And the way that I'm going to express that here is that the volume will be equal to the area of the base. All right, all of the cross-sections of this parallelepiped, at least in this direction, will be the same as the base. So we can take the area of that base and multiply it by the height of the parallelepiped, and that would give us the volume. So we're going to be multiplying the area of the base times the height. Okay, so that's the basic idea. But how do we involve vectors in this? How do we get to the triple scalar product? Well, what we can do is represent some of the edges of this parallelepiped with vectors. In particular, here's how I'm going to do it. I'm going to let this edge right here be vector v, and then I'm going to let this edge right here be vector u, and then this edge right here will be vector w. Okay, now notice that all three of those vectors are starting at the same point, the same vertex of this parallelepiped. They all have an initial point of that vertex and then end at other vertices. Okay, and so these three vectors, vector v, vector u, and vector w, represent three adjacent edges of this parallelepiped. And so now that we have those vectors in this diagram, how can we begin to use them to calculate the volume of the parallelepiped? Remember that we need the area of the base as well as the height of that solid. And so let's start with the area of the base. If you watched my previous lesson, you might be able to figure out this first part. Notice that the base of the parallelepiped is a parallelogram where two adjacent sides are represented by vector u and vector w. And we learned in the previous lesson that we can calculate the area of a parallelogram, where two sides are represented by vectors, by taking the magnitude of the cross product between those two vectors. Right? So if we took the cross product of vector u and vector w, and then took the magnitude of that vector, that would give us the area of this parallelogram, which would be the base of this parallelepiped. And so we can write that right into our formula here. The volume will be equal to the magnitude of the cross product between vector u and vector w. That's going to give us the area of the base, but then we need to multiply that by the height of the parallelepiped. We still need to represent that height using vectors in some way. And so how can we do that? We have the area of the base, but how can we represent the height? Well, as you might be able to guess, it is going to involve vector v in some way. Okay, in order for this volume equation to end up as the triple scalar product, vector v has to show up somewhere, right? Because the triple scalar product involves three different vectors. But it's not entirely clear how we will use vector v. You might be tempted to say, well, maybe we just multiply it by the magnitude of vector v because the magnitude or the length of vector v would be the height. But that would be incorrect. The magnitude of that vector does not represent the height. The height of this parallelepiped would be a slightly different measurement. It's not going to be this diagonal measurement here. Instead, it's going to be the measurement from the base to the top of that parallelepiped. This distance right here, this straight measurement, okay? It's not this slanted measurement or the magnitude of vector v, it's going to be this measurement right here. And if you can't quite visualize that, this would be the same as the measurement from this vertex to the base. So this measurement right here, this would also represent the height of the parallelepiped. Maybe that helps you kind of visualize what measurement we're talking about here. It would also be the measurement from this vertex to the base. Okay, so these two measurements here would also be the height of the parallelepiped. Just thought I'd show you that in case you're having a difficult time visualizing that. But anyway, if this measurement right here represents the height of the parallelepiped, how do we find that height? Well, it's not very intuitive at first, but something that can help us here is to draw in another vector. In particular, I'm talking about the vector that results from the cross product of vector u and vector w, right? The cross product of two vectors is going to be a vector that is orthogonal or perpendicular to both of the vectors involved in that cross product. And so the vector that results from vector u cross vector w would be the vector that looks like this. That is the cross product of vector u and vector w. This vector is perpendicular to both vector w and vector u. It makes a right angle with both of those vectors. And the way that I know that it's pointing upward rather than downward is by using the right-hand rule, which if you're not familiar with that, be sure to check out my lesson on the cross product where I talk about that. But this is the direction that vector u cross vector w would be pointed in. Now it's important to realize that this vector is not necessarily going to be the same length as the height of the parallelepiped. We can't make that assumption. I suppose it could be the case, but generally we can't assume that. The magnitude of this vector is most likely not also going to be the height of the parallelepiped. So instead, what we have to do is relate vector v to this vector in some way that allows us to find this height. And so this is where your knowledge of other concepts related to vectors comes into play. And so I'll give you a second to think about it, but what we're going to end up doing here is finding a vector that would represent this height by projecting vector v onto this cross product vector, right? If we project vector v onto vector u cross vector w, that vector would look something like this, right? We start at the terminal point of vector v, draw a line perpendicular to that other vector. So this angle right here is a right angle. And where that line reaches to this vector will be the projection vector of v onto that other vector. And that projection vector will be exactly the length of the height of the parallelepiped. And so this vector here is the projection of vector v onto the cross product of vector u and vector w. Okay, and so if we took the magnitude of that projection vector, we would have the height of the parallelepiped. And so if we add that to our volume formula here, we'll be multiplying by the magnitude of the projection of vector v onto vector u cross vector w. All right, and so that's the first step in our process of finding a formula using vectors to calculate the volume of this 3D shape. But we can simplify this further. Remember that there is a special notation and formula for calculating the magnitude of a projection vector. Typically, we'll write it like this. Let me just rewrite the first part of this volume equation here. We have the magnitude of vector u cross vector w. But then we can rewrite the magnitude of this projection vector with a different notation. The component projection of vector v onto this cross product will have the component projection of vector v onto vector u cross vector w. It represents the same thing. It's still the magnitude of this projection vector. But then we have a formula that allows us to calculate this component projection, or the magnitude of this projection vector, and that looks like this. We found this formula in my lesson on vector projections. The component projection of a vector v onto another vector u is equal to the dot product of those two vectors divided by the magnitude of the vector being projected onto. So in this case, we'll have the dot product of vector v and this cross product, and then we will divide by the magnitude of this cross product since that is the vector being projected onto. It is the subscript of the projection or component notation. All right, so here's what we'll have. The volume will be equal to the magnitude of vector u cross vector w, and then we're multiplying by the component projection of vector v onto the cross product of u and w, which will be equal to the dot product between vector v and that cross product. So we will have vector u cross vector w, and that cross product is multiplied by vector v via the dot product, and then we divide by the magnitude of that cross product, right? We divide by the magnitude of the vector that we are projecting onto. So we'll have the magnitude of vector u cross vector w. All right, and so now here's the fun part, or the punchline of this whole thing. Notice that we are multiplying the magnitude of the cross product between vector u and vector w by another expression where the denominator is the magnitude of vector u cross vector w. We have the same magnitude right here in the denominator, so those two quantities, or those two values, are going to cancel out. Anything divided by itself is equal to 1, so we just have this right here multiplied by 1. Okay, so this magnitude and this magnitude cancel out and leave us with this calculation, which if you watch the beginning of this video, you should recognize as the triple scalar product. It turns out that the volume of a parallelepiped using three vectors that are adjacent edges of that parallelepiped is just equal to the triple scalar product of those vectors. And so this is just equal to vector v dot the cross product of vector u and vector w. All right, that is what the volume is equal to. And if you want, you can add on one more adjustment here. You might also want to add this. I'm going to put absolute value bars around this calculation because sometimes this might be negative and you can't have negative volume. We always want the absolute value of whatever results from this triple scalar product. Okay, and so with that, that is how we get to this end result that we can calculate the volume of this 3D solid, a parallelepiped, using the triple scalar product of three vectors. And so with that, let's actually take a look at some example problems where we calculate the volume of a parallelepiped. Okay, so here's our first example. We want to use the triple scalar product to find the volume of the parallelepiped having adjacent edges vector v, vector u, and vector w. Vector v is the position vector of the point 1, 3, 1, vector u is the position vector of the point 0, 6, 6, and vector w is the position vector of the point -4, 0, -4. Okay, and so this is pretty straightforward. If we want to calculate the volume of a parallelepiped where these three vectors are adjacent edges of that parallelepiped, all we have to do is calculate the triple scalar product of these three vectors. Okay, and so the volume will be equal to the absolute value of that triple scalar product, right? So we're going to have vector v dot the cross product of vector u and vector w, which will be equal to a 3 by 3 determinant, or the determinant of a 3 by 3 matrix, where the first row are the components of vector v, the second row are the components of vector u, and the third row are the components of vector w. So we'll have 1, 3, 1, 0, 6, 6, and then -4, 0, -4. Okay, this is using that shortcut method that I showed you at the beginning of this lesson. We can calculate a triple scalar product fairly quickly by just setting up a 3 by 3 matrix like we have here, and then taking its determinant. And before we calculate this determinant, something I do want to point out here is that because we're calculating volume, and we're going to be taking the absolute value of whatever this determinant is, it actually doesn't matter the order in which you place these vectors' components in this 3 by 3 matrix. And what I mean by that is you could put the components of vector v in the second row, put the components of vector u in the first row. You can swap the order in which you have these vectors' components, and it's not going to matter. Because when you swap the order of rows in a matrix, the only thing that changes with the determinant is the sign. It might just change by a factor of -1. And so if we're just taking the absolute value of that result to get the volume, it doesn't matter if our answer is positive or negative because we're taking the absolute value of it. And so all of that to say this, don't stress about what order do I put these vectors into this matrix. It doesn't matter, at least not for this when you're calculating volume. You don't have to worry about that at all. All right, if you're just straight up calculating a triple scalar product, but not as a measurement of volume, you're just calculating some other triple scalar product for some reason, then the order matters because you're not calculating volume. But since we are in this case, getting the order right is not a big deal. Okay, but anyway, let's calculate this triple scalar product. This is going to be equal to the determinant of this 3 by 3 matrix. We'll start by looking at the first value in the first row, which is 1. We're going to cross out the row and the column that 1 is in, and then use the remaining 4 values to calculate a 2 by 2 determinant that will then be multiplied by 1. All right, so we'll have 6 times -4 minus 6 times 0. All right, now 6 times -4 is -24. So we have -24 minus 6 times 0, which is 0. And that is multiplied by 1. So we're multiplying by 1. Then we subtract the middle term, which we get by looking at 3. We're going to cross out the row and the column that 3 is in, and then take a 2 by 2 determinant of the remaining 4 values and multiply that by 3. So we have 0 times -4, which is 0, minus 6 times -4, which is -24. So we have 0 minus -24, and that's multiplied by 3. And then we're adding the last term, which will be multiplied by 1, the last value in that first row. So we're multiplying by 1. I'm going to write that in right now. But then if we go back to our matrix, we're going to cross out the row and the column that 1 is in, and then use the remaining 4 values to calculate a 2 by 2 determinant. So we'll have 0 times 0, which is 0, minus 6 times -4, which is -24. So we have 0 minus -24. Okay, but then don't forget, we are taking the absolute value of this calculation. So I'm going to draw in some absolute value bars here. And now if we simplify, this will be equal to -24 minus 0. That's -24 times 1. So we'll have the absolute value of -24 minus 0 minus -24. That will be 0 plus 24. So we have 24 times 3. 24 times 3 is 72. So we have minus 72 because we are subtracting that term. And then we're adding 0 minus -24. That's 0 plus 24 times 1. So we have plus 24. Now -24 and positive 24 cancel each other out. So this is equal to the absolute value of -72. And the absolute value bars will make that -72 positive. So this is equal to 72. That is the volume of the parallelepiped having these 3 vectors as adjacent edges. Okay, and do note that in this problem we weren't given any units, right? We weren't told if we were working in meters or centimeters or feet or inches. We weren't given any units, so we don't really need to add them on to the end of this value, but do know that this is a measurement of cubic units, all right? We are calculating volume, so this 72 is a measurement of 72 cubic units. The units are cubed, okay? So just remember that volume gives you cubic units. Okay, so do make a note of that. You can even write that down behind this answer if you want to. You could say that your final answer is 72 cubic units, and that would be acceptable. Okay, now I do have one more example that I want to look at, but before we get to that example, there's one thing that I want to talk about here, which is what does it mean if we were to find that this volume was equal to 0, right? What if for some reason we calculated this triple scalar product and we ended up with a result of 0? What would that mean? What would that tell us about these three vectors? Well, if you think about what it means for something to have a volume of 0, it means that it doesn't have a third dimension, right? So really the shape that would have these three vectors as adjacent sides wouldn't be a parallelepiped. Instead, it would be some kind of 2D shape that doesn't have a volume, but rather an area. All right, so if the volume is 0, when taking the triple scalar product, you're not working with a three-dimensional shape, you're working with a 2D shape. And ultimately what that implies about these three vectors is that they all lie in the same plane. They are coplanar. And to show you what I mean by that, if I draw a plane here, this plane is a 2D shape, right? It exists in 3D space, but it only has 2 dimensions. And so it's fair to say that a plane would have no volume. It has a volume of 0. And so if we're looking at three vectors that have a triple scalar product of 0, that means we're looking at three vectors that all lie in the same plane. They don't move outwards of this plane, right? So maybe vector v would be this vector right here, vector u would be this vector right here, and vector w would be this vector here. They all lie in the same plane. None of them move outward. We don't have a vector pointing this way that is not in the plane, or we don't have one pointing this way or this way. All three of those vectors are contained within that plane. Okay, so I hope that helps you visualize what we're talking about here. But just to get the point across one more time, here's what you need to know. If the triple scalar product of three vectors is equal to 0, then you can conclude that those three vectors are coplanar. They all lie in the same plane. You cannot create a parallelepiped with those three vectors as edges because they're all in the same plane. They don't allow for that third dimension. Okay, but with that, let's take a look at one more example of calculating the volume of a parallelepiped using the triple scalar product. Hey there, real quick, before we get to the next part of this lesson, if you find my tutorial videos here at JK Math to be helpful and you want access to more content such as exclusive bonus videos and dark mode versions of my videos, I'd invite you to check out my membership site, JK Math Plus, where all of that content is available. To learn how to join and see a full list of everything you'd get access to as a member, you can head over to jkmathematics.com/plus. I'll have a link for that in the description of this video. Okay, so if you're interested in becoming a member, feel free to check that out. It's a great way to support me and the tutorials I make, as well as a great way for you to learn math better. But for now, let's get back to the lesson. Okay, so here's our last example. We want to find the volume of the parallelepiped with the following vertices. And we're given all 8 of them here, all 8 vertices of this parallelepiped. Now, we're not going to have to use all of them because we only need vectors representing 3 edges of the parallelepiped, which are only going to end up using 4 of these vertices. And so let me show you what I mean. Let's draw a picture here. Let's say that this is our parallelepiped. That's the base at least. And then we're going to have something that looks like this. Not a perfect drawing, but this will do. This gets the point across. You can see that we have 8 different vertices that I'm labeling here with these dots or these points. And to calculate the volume of this parallelepiped, we only need 3 vectors, right? We want to choose one vertex and then draw 3 vectors from that vertex. So we'll have a vector here, we'll have a vector here, and we'll have a vector here. Those 3 vectors will allow us to calculate the volume of this parallelepiped. And we're only using 1, 2, 3, 4 of those vertices. There's 1, 2, 3, 4 that we will not use, and so we really have more information here than we really need to find the volume. And this is where things can be a little confusing at first, because how do you know which 4 points to pick? Does it matter? And thankfully the answer is no. Surprisingly, it actually doesn't matter what 4 points you choose to use. That might seem shocking, like that doesn't make sense, but it turns out that mathematically, if you find three vectors from any of these four vertices, and then perform the triple scalar product and take the absolute value of the result of that triple scalar product, you will get the same volume regardless. The only way that you won't get the right volume is if you end up with 0 because you accidentally found three vectors that were in the same plane or on the same face of the parallelepiped. All right, so for example, that would be if instead of using these 2 points for this vector, if you chose these 2 points or these two vertices. So you'd have this vector, and then another vector all in the same face of the parallelepiped. That would give you a volume of 0 because all three of those vectors are on the same face or the same plane for that parallelepiped. Okay, but other than that circumstance, it doesn't actually matter what points you use. It's going to be mathematically equivalent regardless. And so don't get too caught up in the fact that you're given 8 points, but you only need to use 4, and so which 4 do I use? Don't worry about it. The way I typically go about it is to just pick the first 4 points that you were given, because typically they're going to be the easiest to work with, right? We have 0, 0, 0 for that first point, and then 3, 0, 0, 0, 5, 1, and then 2, 0, 5. Those seem like the 4 easiest points to work with when you compare to these other 4 points that we have. I like all of the zeros that I see in these 4 points. Okay, and so let's do this. Let's find the volume of our parallelepiped. And obviously, in order to do that, we will need to find 3 vectors. And so to do that, I'm going to use these first 4 points, and I'm going to label them so it's easier to reference what point I'm talking about. This first point will be point A, the second point will be point B, then we'll have point C and point D. Okay, and so I did say that it doesn't matter what 4 points you choose to create these vectors, but weirdly enough, it also doesn't matter which point you choose to be your initial point. But despite that, I do recommend that you pick one point to be the initial point for all of your vectors, as that will make the process of finding the 3 vectors the easiest that it can be. And so I'm going to designate point A to be my initial point, since it's an easy point of 0, 0, 0, and then create all of my vectors using that point as the initial point. All right, so we're going to have 3 different vectors, vector AB, vector AC, and vector AD. Okay, so let's find those vectors. We want to find vector AB, then we want to find vector AC, that's going to be the second vector, and then we want to find vector AD. That will be the third vector that we want to find. And these are going to be fairly easy to find, because the initial point is just the origin. So if we're going to find these vectors, we're just subtracting these components from each of those terminal points in each case. But if you're just subtracting 0 from each number, those numbers aren't going to change. The components of these vectors are going to be the exact same as the coordinates of the terminal point, right? Because for this vector, AB, 3 minus 0 is 3, 0 minus 0 is 0, and 0 minus 0 is 0. All 3 of those coordinates will be the components of vector AB, just like the coordinates of C will be the components of vector AC, and the coordinates of point D will be the components of vector AD. So that's kind of nice. Since that initial point is 0, 0, 0, finding these vectors is pretty easy. So the components of vector AB are 3, 0, 0. The components of vector AC are 0, 5, 1. And the components of vector D are 2, 0, 5. Okay? Now, what we want to do is calculate the triple scalar product between these 3 vectors. And once again, just like I said earlier, it doesn't matter the order in which you perform this triple scalar product. You could dot product this vector with the cross product of these 2, or you could take the dot product of this vector with the cross product of these 2. It doesn't matter, because when we're calculating volume, we're going to be taking the absolute value of that triple scalar product. And so any change in the sign of the determinant as a result of swapping rows in the matrix isn't going to matter. Okay, and so here's how I'm going to do it. I'm going to take the dot product of vector AB with the cross product of vector AC with vector AD, and that will be equal to the determinant of a 3 by 3 matrix that we're going to set up right now. The first row are going to be the components of vector AB, so 3, 0, 0. So I'll write 3, 0, 0. And the second row will be the components of vector AC, so we'll have 0, 5, 1. So we'll write out 0, 5, 1. And then the third row will be the components of vector AD, which are 2, 0, and 5. So we'll have 2, 0, and 5. Okay, so now let's calculate this 3 by 3 determinant. And remember, we are going to be taking the absolute value of this triple scalar product. So this will be equal to the absolute value of whatever we get here. We'll start by looking at 3. We'll cross out the row and the column that it's in and multiply 3 by the 2 by 2 determinant of these 4 leftover values. So we have 5 times 5, which is 25, minus 1 times 0, which is 0. So we have 25 minus 0 times 3. Then we subtract that middle term, which will be multiplied by 0. And then we're going to be adding the last term where that component will also be multiplied by 0. So that's kind of nice, right? We actually don't have to go through these last two terms or these last two 2 by 2 determinants because we're just going to be multiplying them by 0, right? You always multiply by that value in the first row. We multiply the x component by 3, the y component by 0, and then the z component by 0. And so these two values are just going to become 0. So I'm not even going to bother with calculating each of those 2 by 2 determinants because I know the end result is going to be 0 since we're multiplying by 0. So all we're left with here is 25 minus 0 times 3. And so we'll have 25 times 3, which is 75, which means that this will be equal to the absolute value of 75, which is just 75. 75 is the volume of this parallelepiped with these 8 vertices. Okay, and do remember that those would be cubic units since this is a measurement of volume. So I'll write cubic units. All right, and if you wanted to, you could check what I said earlier, try finding 3 different vectors using these vertices, and then take the triple scalar product of those vectors, and you should get the same result of 75. The only time that you won't get that is if you get 0 because you created 3 vectors that were on the same face or in the same plane of the parallelepiped. Okay, and so with that, that is it for this lesson. But if you do want to see some more examples of calculating the triple scalar product and using it to find the volume of parallelepipeds, feel free to check out my examples video that I'll have linked here on the screen. If you have any questions, feel free to leave those in the comments. But if you don't have any questions, this is all I had for now. So I will see you next time.